Can you try again, please?
Yeah, now it's working, thank you.
Okay, so just again, for the video, so last week, we were considering a model-based feed-forward control, namely, which is we have the plant, some model of the plant, and we're trying to use this model exactly to actually invert the plant, which means we want to follow a certain trajectory, so a certain demanded output over time. So what is the necessary input to achieve this? And this is what we did. And on top of that, of course, any kind of algorithm that is able to achieve this will also tell us what the output actually is, which means as a consequence, we can use this output. And then we arrive here at 2 degrees of freedom control, which is if we know the output that would result from our input, and if we told any kind of feedback controller to track exactly this output, and in the ideal world, the control error, which is y star minus y, it's exactly equal to 0. So this controller is actually jobless. The only point in time where this controller has to work is when there is a disturbance or if there is some mismatch in the parameters of the plant. And then, of course, and this is the reason why we call it 2 degree of freedom control, this controller can be designed deliberately in order to compensate disturbances. You might be satisfied with a very slow disturbance compensation, for example, whereas this part of your scheme is only designed to follow references. So you have 2 degrees of freedom to design separately disturbance rejection or reference tracking. This is the reason why we call it 2 degree of freedom control. Yes, please.
I think we don't see anything.
I'm sorry. Okay, then something went wrong. Okay, I have to share again.
Yeah, thanks.
Okay, so this was all about this figure, obviously, here. And in the presentation I'm going to show you later, you will see that this is very important, especially when it comes to nonlinear systems, because the model-based feed-forward control might drive your system into an operating region where your controller, which is based on linearization, for example, works, or in another region where it doesn't work. So this is very important to note also. So let's go on a little bit. How did we do it? And notably, I showed you how to achieve this with systems of this kind. So this is a nonlinear state space system, which is input affine. And then we have a certain output. And the way we did it follows exactly the same idea as feedback linearization. So the first step is always to apply a transformation. So we take the output as the first transformed state variable C1. We take the derivative of the output. You probably remember it by now how to do this. And we proceed to carry out time derivations until we arrive at Cn. And then when we carry out the derivation once more, we get the nth derivative in time, which we call Cn dot, or we also like to call it the new virtual input. And you probably know how this game works. So we have these Lie derivatives. And now in terms of feed-forward control, we look at it differently. We assume, this is very important, that at one point in time, I'm just skipping a few slides here. We assume that at one point in time, namely at t0, we know exactly the state vector of the system. Normally, if you take any system, we start it from rest. You will see this in the examples today, so you don't have to measure it. If a system is at rest, if any velocities are 0, then you know that normally the state vector is also 0. Normally, you don't have to measure it. You can also guess it, or you can guess it from a few measurements. So then we call this x star of x0. So this is x star, which is our state vector, which is comprised from our demanded value. So you see everything which is denoted by a star is a demanded value. So we do not only prescribe a y, but also its derivative. So this can be seen as a trajectory of the system. So from the inverse transformation, we know our demanded trajectory x star. And from, now I'm going back to this equation, from this very last equation, we can read this in either direction. But in this case, we see, okay, there's a certain demanded value also for the nth derivative, which is here. And from this, and of course, from knowing x star, we are able to compute the input y, which is required for the system to follow exactly this trajectory. So these two equations actually constitute The manipulations, the calculations that you have to do, you can do them offline or online in order to steer the system. And I've just illustrated this by this figure here. So you see that obviously there's the output of the system, there's our input, and you could see it in such a way if you want to invert the system. So if you want to answer the question, I want a certain output to be tracked, what is the necessary input? Then you have to provide not only that output signal, but all its derivatives, which are here. And then by providing the signal, you're able, so to say, to invert the system, to compute the necessary input to achieve a certain output. This is what we call inversion of systems, of dynamic systems, okay? So this works for every system, if you want, so that has full relative degree. And of course, it also works for linear systems in particular. And this is what we are going to look at right now. And we're going to look at an example. In particular, if you express everything for linear system, it turns out that our transformation, that is of course only a transformation matrix, so t times x, it's a lot simpler than for any nonlinear system. And the transformation matrix is made up of the observability matrix. And obviously you can see here, in order to compute the control law, you need to know the inverse, which means that this matrix must be invertible. And obviously, this is only possible if the system is observable from the chosen output. So if your output is not, if your system is not observable from the chosen output, you cannot compute the inverse, and then it doesn't work. So it doesn't work for every output, notably, okay? So everything works pretty much the same. So the only thing you have to do is compute your reference trajectory, compute all its derivatives, line them up in this vector here, left multiply them by the inverse of this transformation matrix, then you get x star. Once you know x star, you put it in here. You use it in here. You also have to know the nth derivative of the desired output, and then this actually determines what the required input is. This is actually very simple procedure if you want so. I've mentioned now, even today, several times that you need to know y dot, y, all the way through the nth derivative of y in order to do that. So normally, up until now in our control lectures, we only had our reference signal, which we denoted by w, and most often w was a step sequence in order to check how our controller reacted. But right now, we have to go a little bit further. We actually have to plan our trajectory. So just imagine, and I'm going to show you a video right now. This is the lab experiment that we are going to look at today. So this is a servo unit with an electric motor. It's a little bit blurry here, but you can see it. And then we have a base unit, and on that base unit there's a rod. It's connected through a joint, and there are two springs. And obviously, this system has oscillatory behavior. So when you apply step signals on the voltage, it just moves in the way you see it here. And our goal today for the system will be to move this rod in a very nice fashion, just to move it from here to say to a 90-degree turn in a very, I would say, smooth fashion. So in order to do that, of course, this is only a lab experiment, and it's very simple, but it represents typical systems that are encountered, for example, in robots. You might also see them in car suspensions, for example. So whenever there are masses and there are springs, you get oscillations. And if you really want to move that rod from here to there without any oscillations, then you have to plan your trajectories. What is the way you want to move this rod from here, say, for example, to there? And this is something that we have to consider separately. There are many different ways to do it. I've shown you some ways last week. So there's a very simple way where we assume that we actually start from an initial position y0. We want to end up at a terminal position, and it should take us capital T seconds to do that. So there's one very nice recipe which you can find here. So it's actually a polynomial, which is good because apart from only knowing y, you also have to know y dot, y double dot, and so on and so forth. So we have to achieve an n-fold differentiable signal. So taking the time derivative of this is pretty easy. I don't have to tell you. So this is a very nice way to do it. And obviously there are also other ways. And in this lecture, we're only going to show you this. So you see it's a sum of polynomial coefficients, which are denoted by pi. And for certain orders of systems, as you can see here, we just provide these coefficients. So for you, and then of course it's very nice because not only are we going to start here at y0 and then end at yt, but we're also going to give the system a smooth start. So all the derivatives are 0 when we start, and all the derivatives are also 0 when we end up in the terminal position. So this is nice also in terms of actuators. Everybody wants a smooth system, obviously. So this is a good way to do it. And you see two reference sample trajectories. One is for n is equal to 1. The other one is for a fourth order trajectory. And then you might want to play around with this, of course. Now let's start with this flexible link as an example, okay? So I'm going to give you some clues on how to model that system, and it might be probably a good homework for you to try this at home. Maybe recapitulate mechanics, equations of motion. Obviously, it comprises 3 different parts. This is the base unit, which we call the servo. We also use it for other experiments. You are going to see this in your lab class because we are going to use it to drive an inverted pendulum. So you're going to see this again. Then there is some kind of base, which has an inertia, of course. And then we have this rod here, which is mounted by this joint. And then we have some springs that cause this vibrating behavior, okay? So this is a simplified sketch of the system where you have all these parts. We denote the inertial position of the base by phi. So this is the position of this base here, of course. And then there's the angle alpha. And notably, this is an angle relative of the rod with respect to the base. So it's not an absolute angle, but it's a relative angle. So by now, we're able to say if we want to control the position, the angular position of that rod, we have to be able to control the sum of these 2 angles, okay? So we're not only controlling alpha or phi, but we have to control the sum of both. So how would we get the equations of motion? Obviously, we have a mechanism which comprises 2 parts, which are shown here again, okay? So this is the base, this is the rod. Then we assume that we actually know the torque, the electric torque that is exercised on this base by the servo. You will see this also in the lab class because it's the same unit, of course, okay? Then we assume that the springs, obviously those springs, they're non-linear, but for right now and for the sake of simplicity, we assume that this is a linear spring with a certain stiffness, okay? And in your lecture notes, you find, in your handouts, you find all the parameters, of course. This is the equation for the torque, okay? And it's typical that the torque, of course, how are we going to control the system? We apply a certain voltage to the electric motor. And of course, the torque it's more or less proportional to that voltage, but it's also decreased if there is a certain angular speed. This is typical of electric motors. If there is already some rotation, which is denoted by phi dot, then of course the torque is decreased. So this is our equation that we have to use. And now for your ease, we are going to model the system by the Lagrangian equations, which you probably remember from mechanics courses. These are the Lagrangian equations. We have 2 degrees of freedom of motion. This is phi and it's alpha. So it's the motion of this base box, if you want. So, and it's the motion of this rod relative to the base. This is what we would choose as the degrees of freedom. And then we need the kinetic energy of the overall system. I'm going to point this out. That's the kinetic energy. And we need the potential energy. And we also need the so-called generalized forces. I'm going to explain in a minute what this means. So setting up the overall kinetic energy, it's pretty simple. So we have the some inertia times phi dot squared, obviously. And then we have the inertia of the rod, which is given here, times the sum of these 2 angular velocities. That's the kinetic energy. There's potential in the system, of course, and this is in the spring. So every force, if you remember from your mechanics courses, every force which is conservative, and this is true for this spring here, has a potential. Also, like if we would take the overall experiment and tilt it, then we would probably have the pull of gravity here, which would make things even more complicated. We don't do it by now, but the force of gravity definitely also has a potential. In this case, it's only the spring, which is here. So it's 1/2 times the spring constant times alpha squared. And then we are arriving at the generalized forces, and they are normally determined through the so-called virtual displacements. You probably remember this from mechanics courses. We are assuming that we take this overall mechanism. Let's assume that it's in a certain transient motion. So there is some angular speed here, some angular speed there is some motion also. And at some point in time, we just freeze it. Like if we took a photo, we freeze it. And then we make virtual displacements of this base unit. And we make a virtual displacement of this rod. And then we know that there is a torque acting on the system. We also probably know that there is some dissipative forces. And now we determine what kind of work is carried out by those forces. And then by comparing them to this equation here, we get an expression for the generalized forces. So in this case, there's actually no damping in this joint. So we assume that this rod is connected in a frictionless joint. However, we know that this base plate, let me return to this here, this base plate is connected to the servo, and there is some damping, there is some mechanical damping, and there's also some electrical damping because there's internal electrical resistance in the system. So I'm just keeping this short for you. Overall, so if we move the system by a small virtual angle delta phi, so moving the base, I've just denoted this, then we have the torque, which is a positive work, minus the damping forces, viscous damping forces. And if we compare this to q phi times phi, so this is the generalized torque, which is associated to motion of phi, then obviously we know what it is. Secondly, if we freeze the motion and if we just move the rod, we see that there is no further force. Of course, there's the force of the springs, but we have already considered that in the potential. There is no further forces, so obviously this is 0. And then by doing all this, we get this bunch of equations. So you see, it's already nice, but still we need to solve it for phi dot and alpha dot, which we did here. So I'm just doing this in a very fast fashion, but I really ask you to try this at home, because it's always good to be fit in equations of motion and just repeating this every now and then. So just try it at home and check if you manage to do it, because in the lab, you will have to do it for the inverted pendulum. It's a little bit more complicated there, but you will be able to do it so. Okay. So there is a number of abbreviations. And now we choose the state vector, and obviously the state vector is chosen as the two angular displacement and the two angular speeds. That's what we need, obviously. And then we arrive at such a state space system. It looks like this. So you see there are lots of zeros. The first part of the state space simply tells that the derivative of the first two states are the second two states. This is what we get from this upper block here. And the lower block is simply our Lagrangian equations, if you want so. Okay. Our input is the electrical voltage that we apply to the servo unit. And again, our output is the sum of phi and alpha. This is what we want to control. Okay. There's a bunch of parameters which we determined from the experiments. And then this is what we're left with. These are the numerical values of everything, okay? So the first thing we have to check is, if we choose this output, which is the position of the rod, then what is the relative degree of that output? And let us check this here. Very simple. Let me go back to the theoretical part. And obviously, in this case, we have to carry out this check here, okay? So whether all those expressions are 0, save for that one, which is corresponds to n-1. And then we take the transformation matrix. So let's carry out this check. It's done down here. See here it is. So C times B is 0, C times A times B is 0, C transpose times A squared times B is 0. We have a fourth order system. So that expression needs to be different from 0, which it is. So very easily we arrive at our transformation matrix. So this is actually everything that we need. So the whole feed-forward controller is pretty much a handy one. If I just go back to that and show it to you again. The only thing that we actually need to compute from our matrices is the T matrix. Everything else is already available. So we need the T matrix, or more precisely, its inverse. We need A to the nth power, A to the n minus first power, of course, C transpose times this matrix times B, and then we are done. That's actually all that we have to do in order to execute the control law. There is something else that we have to do. We have to find something on the reference trajectory, which I would like to show you. So how to compute the reference trajectory. And this is here. So we have a fourth order system. And this is just one example. And we are going to send you some MATLAB code where everything is done for you, and then you can play around. So for our video and our example, we assume that everything is at rest at t is equal to 0. So when we start everything, so it's 0. We want to make a 90-degree turn, counterclockwise, of course. So it's p over 2. And then we want this to be carried out in half a second, which is pretty fast. Okay, if I just show you the video again. So this is in real time. So you see, this is probably also about half a second, and you can see by turning it so quickly, you will get quite an amount of vibration in the system, which you do not want to see, of course. So 0.5 seconds, and this leaves you with this kind of trajectory, which you can see here. So you can see it takes 0.5 seconds to reach this value, and obviously carrying out the time derivatives, you need all the derivatives up to the fourth one, and this is pretty easy to be done, obviously. Okay. So let me show you first some MATLAB simulations, and this is the stuff that is also going to be provided to you. So one of our assistants made this very nice. So I'm just starting this. So we choose the end time, which was 0.5 seconds. Okay, 90 degrees. This is what we wanted to have. And now there is a slow mode. Can you see this nice? Can you see this well?
Yes.
Okay, I'm going to run it again for you. So what you see here is obviously there's an animation of everything, a slow motion animation. You can see in red, this is the angular position. There is actually the arm and the base have been juxtaposed, so it has to be corrected, obviously. But you can see very clearly what happens to the base and to the arm. So there are some oscillations in the base, which is necessary to twist the springs in order to get the arm moving. I'm going to play it again in a second. And this is our necessary control input. So let me play it again and really pay attention to the movement of the base and to the movement of the arm. So it's 0.5, 90 degrees. So you can see this controller really needs the base in order to twist the springs in order to get this arm moving, and the arm does exactly what we want, namely it actually moves from 0 to 90 degrees in a very nice and smooth fashion. Let us just play around a little bit. What happens if I give it more time, so 1 second, which is pretty easy. You see, this is a pretty easy job for the controller. We can go even one step further. Let's try 2 seconds. So this is really slow. Okay, and now obviously we can also go into the opposite direction. So let's try this much faster, like for example, 0.3 seconds. So you see now there's a lot of twisting required, and of course the actual system wouldn't work because there is some detent, so you cannot twist it indefinitely. But you can see still The arm movement is very nice. It's very smooth. And the base has to twist, really has to twist a lot in order to get this working. Okay.
A question.
Yes, please.
Is it possible that on the graph the legends are switched? So
yes,
instead
exactly.
of
I
R
just mentioned this before that.
Oh, okay, sorry.
Yeah. Exactly. So we have to correct it. We just finished it yesterday evening, and this was just a mistake. Okay. So obviously next week when it's finished, we are going to send it to you, and then you can play around with it and then have some fun and then play yourself. What I want to show you, this is not only theory, it also works in practice. So there is a step response. Okay. There should, so this is the pure feed forward control. Okay, let me play it again. So that's the pure feed forward control. You see it works pretty nicely. Still, as opposed to the pure simulation, there is some oscillations when the system comes to the end position. You can already tell from the title, this is pure feed forward control. This is, I'm sorry, it's the wrong video. That's the one that I should show you. So you see it works nicely. However, there is some movement in the end position, obviously, and you can hear this. I'm going to play it again. There is some play in the gearbox. Okay, you can see this rattling noise. There is some play in the gearbox, and also there's some play in the springs. Of course, we didn't model it. And this is the reason why once the system is in the end position, there is some residual oscillations, okay? And this brings me to the second part. Of course, in your book, in your handouts, there is some result here. So you can see here in red, this is how the system should behave. And this is how it actually behaved. So there is some deviation, obviously, because we were not able to model the system perfectly. And this is the real life. You're never able to model a system perfectly. I just mentioned, I think 2 weeks ago, all models are wrong, but some are useful. So you'll never be able to model the system perfectly. So what we did is we made it a 2 degree of freedom control stuff. So we added some feedback control here, which was simply a state feedback controller. So there is no further mention on how this works. You probably know it from the previous lectures. So this is how the system behaves without any feedback control. And then obviously if there was some controller, some feedback controller, this would be the control error the system gets. And of course it would take some control action in order to compensate this. Also pay attention to the input signal. So this is our feed forward control. It looks pretty similar to the stuff that you already saw in the simulation that I've shown you. So it probably takes about like half a second to reach this. So this is the pure feed forward control. You don't need any measurements from the system to compute it. If there is some feedback control, and this is what you see here, then obviously everything is much more accurate. You can see this here. And now I'm going to play you the right kind of video. So this is with the feedback controller. Let's make the comparison. So you see it stops immediately. It's very accurate. And you can also see this from the figure. And this is the actual control signal. So you see the dashed red line, that would be the pure feed forward control. So that's the U star that you already know. And the blue one, that's what the controller does. So you can see there is a lot of rattling, obviously. And once it comes to the end position, it actually eases off. And there's another kind of sawtooth signal. And this is mainly due to dry friction. So whenever there's dry friction in the system, it's always a little bit difficult to handle it. So you can see here, obviously, the controller just pushes the system in the right direction. And then the controller tries to counteract some of the friction, obviously. So there's a lot of friction and also play in the gearbox, and the controller tries to compensate this, okay? Let me show you also a slow motion type of video, which is here. And now you can see exactly what you saw in the animation. So this was the kind of type without any feed-forward control. I'm going to and just pay attention. Once the rod reaches the final position, there is some residual oscillations because we were not able to compensate for the play in the gearbox and the friction. Let me show. Should stop and there. For systems with full relative degree, now the question comes, and you already know it, what happens if we want to feed forward control a system that has not full relative degree? And this is the second part of this chapter, and it's covered here. So again, now I'm only going to cover it for linear systems. It's a lot more complicated for nonlinear systems, but the idea is the same. So you already know if a system does not have full relative degree, there is a couple of options. And one of them was the dynamic extension algorithm, for example. One option was to create new transformation equations. You probably remember, if we don't have full relative degree, we are not able to formulate all those transformation equations. Now here what I'm going to show you is another trick. And this trick is compared to the overall history of control theory. This is pretty new. It was only invented in the 1990s, like 25 years ago. And this is the so-called flat output. I'm sorry, I didn't want to cross it out. I didn't want to strike it out. The so-called flat output. So this is another idea. Let's assume that we want to control this system. And we just found out our output, which is called y, does not have full relative degree. So already when we formulate this expression here, it's different from 0 for a data which is less than n, okay? So one idea would be the following. Let's assume that we were able to formulate a new output, a so-called virtual output. Thus far, we were only able to formulate virtual inputs. Now let's assume that there's a virtual output, which is, of course, every output in the linear system needs to have an output vector, an output matrix. And now we call it lambda. And for that virtual output, we wanted to have full relative degree. Now, in order for that to be true, obviously that matrix, that output matrix, the output vector lambda, has to satisfy exactly these equations. So lambda transpose times a to the ith power times b should be 0. all the way to n-2 here, and only for this last is equal to E transpose times QS to the -1. So there are two things to be said right now. First of all, this operation here can only be carried out if the inverse of this matrix exists. And I assume that you probably remember from previous lectures that the inverse of the controllability can be only found, it only exists if the system is fully state controllable. So item 1 that we see here, if we want to find some virtual output which is flat, which has full relative degree, as we call it, it's only possible if the system is fully state controllable, item 1. And secondly, we see that we get a virtual output vector, which is called lambda transposed. And from this, we will be able to formulate a new output of the system that has full relative degree. Now, if you think of this, when I heard this myself for the first time, the first question that came to my mind was, well, how does that output look like? Because if we have any kind of system, for example, this flexible joint system, for example, then what other output could I think of that has the property of full relative degree? And this is the funny thing. This so-called virtual output can be anything. It can be a very abstract thing that has no physical meaning. However, there are some systems, and I'm going to show you one in a minute, where this output has a very hands-on, a very practical meaning, which I really like a lot. And then I'm going to show you another example, which is an aircraft, vertical control of an aircraft, where this also would have a very practical meaning, okay? So what I've shown you thus far was actually no solution to our problem. If we have an output, and if we want to control that original output, which is here, nothing has been said about how could I control it. The only thing that I've shown you so far is how could we find a new output for that system that has full relative degree, and we have found that. So there is some kind of recipe. The system has to be fully state controllable. And in principle, if we find some kind of correlation, some transformation between our actual physical output and the flat output, we could use it in some way to relate each other. So if you're able to relate the physical output to the flat output and vice versa, then it would be probably pretty easy to control this flat output instead of the physical output. And then everything I've told you thus far would be applicable. And this is the reason why the flat output is something which is vastly used also in industry when the system does not have full relative degree. Let me show you, okay, maybe let's just conclude everything. Once we are done in finding this flat output, everything else I've shown you thus far applies. So we apply the system transformation. We are able to compute all those transformation equations. Everything is nice and neat. And then once we know the trajectory, the reference trajectory of the flat output, we are able to apply the control law that we just heard about a minute ago, okay? Now I'm going to show you an example that shows you very clearly how this flat output could relate to the physical output and vice versa. And this is something that you are going to encounter very soon, which is the inverted pendulum, okay? So let's assume that we have this kind of physical setup. So there's a card, which is here. It has a mass m, okay? And in the first step, we consider the card position S as an output. So we assume that this inverted pendulum has to be balanced. Of course, it should be balanced in the vertical position. And then we want to move the card. We want to move it right or left, so to say. And you probably know it. You can try this. Normally, if I was in the classroom, I would take some rod. I normally take an umbrella, and I show everybody how to do this. And probably you should try it at home. And we assume it as our input. We assume as our input to be this force denoted by U. And obviously then the rod has a moment of inertia, it has a mass. And then of course, there's a second state variable, which is theta, which is this angular position, which we also have to control. So we don't want this rod to just dip down. We want to keep it in the upright position. Again, if you want to do this, so we have two generalized coordinates, which are given here. You can apply the Lagrangian equations, and I recommend you to do this because for the lab class, you will have to do it for our rotary inverted pendulum. So in our case, we don't have this rod, but we have the servo unit with another base where there's an arm and this rod is mounted. So you're going to see this soon enough, and then you will have to control it. So this is a very nice experiment. In our case, it's a translatory system. So these are our two differential equations. And of course, right now, for the sake of simplicity, we are going to linearize them around the vertical steady state position, which is this one. And this is our state vector here. And this will be your state space system. So you see what we're going to control is the first state, which is the card position, okay? These will be our state equations. And of course, there's a number of parameters which are given here. When we see the, when you check for the full relative degree of this output, which I didn't do here, but you can do it at home, you will find out that S, so the card position, does not have full relative degree, should be mentioned here, okay? Does not have full relative degree. So what we have to do here in this example, we are looking for a flat output. So you can see any output of the system can be formed using S, the position of the card. It can be used. It can be formed using the position of the rod, and it could also be used we could also use the angular velocities. So you can see if you had a linear combination of all these four, it would be rather abstract. So I'm not able to imagine some kind of physical meaning if you combine all those state variables, okay? But for now, let's just give it a try. Let me just repeat what we have to do. We have to look for lambda, and lambda, this the output matrix of our flat output is found by taking this this vector E, which is 0, 0, 0, 0, and 1 times the inverse of the controllability matrix. So let's first look for the controllability matrix. So we formed it here. So this is a general way how to do it. And we also use the scaling factor. In this case, we didn't choose it to be 1, but we chose it to be like this. And this has a certain meaning in this example, okay? So the scaling factor was not 1, it was like this. And then, of course, our vector E looks like this. And because of this choice, if we take the inverse of the controllability matrix and left multiply it by E, you can see it here, you get this here. So you can see our output vector for our virtual flat output, and you can see this is actually unique. So once the linear system is controllable, the so-called flat output, the output with full relative degree as we call it, it's a unique choice. So there is not like, it's not like that you would probably get 2 outputs or choose between 3. It's just 1, regardless of the system state. I forgot to mention this. And you can see right now, in this case, this is 1 times our first state, which is S, 0 times the speed, and then 2/3 times the length of the rod times theta. So let's take a closer look at what this means. So obviously this is our flat output is S of t plus 2/3 times L times theta of t. And this has a very straightforward physical meaning. It's actually exactly this distance. Of course, everything is linearized here. So we assume that the card has moved a certain distance S. Then we have a certain angular deflection here. So let's assume that there's a virtual point P on this rod. You could think of a red mark, a red dot. So this is 2/3 times the length of this rod. And the flat output is exactly the distance that this point has traveled. Okay, so this is a very hands-on interpretation of the system. And what I want to point out, this system and the position of this card does not have full relative degree, simply because this system is, as we call it, non-minimum phase in German. So for everybody who has attended the Grundlagen der Regelungstechnik, das ist ein System mit Altpassverhalten, so this non-minimum phase behavior. And you probably all know, if you balance a rod, and for example, like if you're here and you balance it, and you want to move to the right, then before you do that, you have to first of all move the rod to the left a little bit. So in order the card to the left a little bit, in order for the rod to tilt over, and once it is tilted to the right, only then are you able to move to the right. Okay, and let me show you what happens with the control. Okay, so obviously what we see here is, if instead of the card position, we control the position of this point here, then we get an output with full relative degree, and everything that we have learned in terms of feed-forward control, and also, of course, we need feedback control for the system, works. And I think it's a good compromise. If instead of the card position, we control this point, I think this is an acceptable choice, because obviously, if you want to control the card position, for example, to move exactly here, and if we stabilize the card, then this point P is exactly above this point of the card, which means by controlling this flat output, we simultaneously control the card position. So this is pretty much a nice choice, so to say. What we have to do is, we have to compute the transformation matrix, and everything else follows immediately. So we apply the control law. So I just give you the final result, and maybe it's a good homework for you to try this by yourself. But it's interesting to observe how the control law looks like. So this is Y star. Y star is equal to, there is the sum of the masses of both the cards and the pendulum times the second derivative. So this, to me, does not come as a surprise. If we want to move the cart and the rod to the right, for example, then we have to accelerate a certain amount of mass. So this is the momentum balance. In German, it's the Schwerpunktsatz. So we have to move both of these masses at a certain acceleration. So obviously, this is the amount of force that is used to do this. And secondly, of course, we and this is not so obvious. We want to move we have to care for this rod not to tilt over in some way. And this is the second part. So it's the fourth derivative. This is not so straightforward anymore. It's just the fourth derivative of the output times this expression here. Okay. So obviously you need to have the fourth derivative and the second derivative. So you have to know them in order to be able to compute this feed-forward control law. And then, of course, it's like, because this is an unstable system, only applying feed-forward control would not be enough in this case. You would also have to apply some feedback control law. Now, I want to show you a very interesting comparison. Namely, if we apply this control law and if we move this point on the rod, which is the flat output, let's observe how this point moves. Of course, we have to find a nice trajectory, so like the polynomial one. And let's compare how this point moves and how this cart moves, okay? And here you see it. First of all, that would be our flat output, okay? So we just designed a nice trajectory. So it took us like 1.5 seconds to move from 0 to 1, like a meter forward. And this is the cart position. And you see exactly what happens here. And this is what I already predicted. If you want to take the cart and move it to the right, then first of all, you have to move it to the left a little bit in order for that rod to tilt to the right. And only then you are able to move to the right. And then if you want to stop, you have to do the opposite. Okay. And what you see here, this figure here is the output of the nonlinear system. It's a kind of stroboscopic plot, if you want so. So you see when we start, so it's a little bit difficult. I'm trying to zoom in a little bit for you. So you see, this is where we start, okay? And this is where we stop, okay? So first of all, you see we move to the left a little bit. And by moving to the left, you can see that eventually this rod tilts to the right. Of course, this is very exaggerated. It wouldn't work in the real world like this, okay? It's just for you to see very clearly what happens. So the rod tilts over to the right. You are moving to the right, and then at some stage it's in the vertical position. Right now, the cart actually overtakes the rod, if you want so. So it overtook the rod. And then at some stage, it just stops here. So the rod still catches up. The rod moves upwards, the cart moves back, and you stop. This is roughly, if you want so, how it works, okay? And this was the rod position. So the rod position was some kind of oscillatory. So this is what we call non-minimum phase behavior. If you want to move that direction, then first of all, you have to move theta in the opposite direction. And now let's take a look at the flat output. Let's assume that we actually marked a red dot on the rod like this. And then we had our camera and we just made a kind of sequence of images. And what you can see for the flat output, of course, it just bends down because the length of the rod is limited. But what you can see is that we actually have a more or less monotonous behavior. So this point on the rod does not move to the back and then not move to the left and then to the right as does the cart, but it has a kind of monotonous movement to the right and then it stops here. So you see, this is the flat output. And obviously, if you understand the physics of the system, and you can really try it at home if you have an umbrella handy, there's no way to carry out such a motion, so to take this base and move it to the right without priorly moving to the left and then stopping. There's no other way because this is the physics of the system, okay? This is the reason why we have non-minimum phase behavior. And this is the reason why the position of the cart does not have a full relative degree in principle. Let me show you one other very nice example. I just found this on YouTube today. So you see here, I'm just about to start this YouTube video, and it just explains so that the blue figure here would be a normal response, and this is the non-minimum phase behavior. So it just goes to downward first, and it goes upward. Okay, and there's a very nice example. If you don't hear the the narrator, then just stop me immediately, because I don't know whether it translates via Zoom to your audio. So just stop me if you don't hear anything.
And how it impacts our ability to control it. We encounter systems that initially move in the wrong direction all the time, even if it's so insignificant as to not be noticed. A classic example is pitching an aircraft up to increase its altitude. When the elevator is deflected up, this causes a downward force on the tail, which provides the nose up pitching torque. And that downward force, however, also pulls the whole aircraft down, slightly lowering the altitude before the airplane has a chance to rotate and increase the lift from the wings. So if you pull back on the control stick, the airplane will drop slightly before heading back up in the direction that you intend. In this case, the dynamics of the system itself has a right half plane 0, and we need to be aware of that when designing a pitch controller for it. And we're going to come back to this idea in just a second. For the aircraft, the dynamics were the cause of the right half plane 0, but sometimes the feedback controller is the one responsible for that 0. Think about the case with a control system that is trying to balance an inverted pendulum on a cart, while at the same time moving the cart to a particular location. To move the cart to the right, the controller first needs to move to the left to get the pendulum angled correctly, and then move to the right.
So you see, very obviously, there are many practical systems. So the aircraft example, you will encounter it very strongly when you travel in an aircraft and you sit in the rear. You see it very often when the aircraft starts to accelerate and lift off. Then first of all, you will really feel this downward motion and then go upwards. And this non-minimum phase behavior and the idea of flat output is also important for the control of the aircraft, of course, and for the way pilots actually are able to control it, okay? So there's one last section, sorry, which is about how to relate the actual physical output, sorry, to the flat output, which is given here. So normally this looks like this. This is just a number of matrix manipulations which you would like to look at. And what you can see here is that the relation is actually that one. So you can see that the physical output eventually, it's the flat output, but it's also a linear combination of its derivatives, okay? So this is the way how this is actually done. Okay, good. So this is all as for the lecture. There is one chapter which is about backstepping control, which I didn't cover, and it's also not going to be covered in the exam, which doesn't mean that you should not take a look at it probably. Backstepping is a nice thing when you arrive at control systems with nested dynamics. So we just decided to leave it in there so that you have some kind of glossary or I would say backup whenever you encounter such systems. Okay. So as I promised you today, I would also like to show you some presentation about why and how nonlinear control and 2 degree of freedom control becomes important and actually vital. And this was this one video, which I already mentioned. Let me just play this again. And this is about fire safety in motorway tunnels. So in motorway tunnels, and Austria is a hilly country, so we have lots of motorway tunnels. The problem really is when you have an accident like this, that whenever there is a fire, and when you just the way you probably remember it from the Grundlagen der Regelungstechnik, which was actually PI control with phase marching. So this was Phasenreserve, if you remember it from German. So you probably know this way of controlling it. This is a way of controlling or designing controllers in the frequency domain. So depending on certain controller configurations, you get more or less phase reserve and overshoot and so on. And then they did this for the controller, and then there was a kind of commissioning test, which was an Abnahme test. So there were people from the ministry, and they actually lit up a fire. I'm going to show you that in a video later on. And then the controller has at most 300 seconds in order to get the flow regime to a steady state where everybody can leave the tunnel. But in this case, it failed completely. So everybody was actually really running for their lives, literally. And then they called me and said, okay, what's the problem here? What could we do about? And then I found out, and I'm going to show you this. I'm not going to show you all the slides because it would be way too much. But first of all, I'm going to show you how to model this. It's a very complicated system, a tunnel, but it can be actually modeled very easily. And then we found out that in certain operating points, it cannot be linearized at all. So this is a linearized controller. It cannot be linearized, and we had to do nonlinear control. And then we proposed them exactly this, what I showed you today, which was 2 degree of freedom control. Let me show you very briefly what happened. This is something what we are actually looking at. This is a kind of commissioning test. So you can see there is some fire. It's actually controlled fire, and you have all the firefighters, of course, to put out the fire. And what you can see here is actually what they call backlayering. And backlayering means that the hot fumes actually go up, and then they collect on the ceiling of the tunnel. And then, of course, on the ceiling, they actually move sideways, pretty much like a mushroom. You probably know what happens if a bomb goes up. You actually get this kind of mushroom. And at some stage, as the fumes leave the scene, they actually cool down. And if they're cool enough, they're actually sinking because they're cooling. And then at some stage, if you have some pressure here from the ventilators, if there's enough pressure, then those fumes actually move backwards. You actually have 2 layers of smoke. One layer, which is invisible here, goes into that direction. Then it changes its direction, goes downwards a little bit, it sinks a little bit, and goes the other way around. So if the pressure is just right enough, and this is the control problem in controlling this, you get something like this. You will see this in the video right now. And then you're virtually able to walk underneath the smoke, and you're not harmed in any way. You don't need any protection in that situation. This is how it should be. And obviously, you need some kind of actuators, and this is seen here. So these are the typical vents that you see in a tunnel. And this is the controlled fire event. So this is some kind of basin where we have some gasoline and diesel. So this is like a big Molotov cocktail. It's prescribed by the law how much of that Molotov cocktail should be incented in order to test it properly. And of course, you also need, if you want to have 2 degree of freedom control, you need to measure air velocity. And this is what you probably also know from aircraft. This is a Bitot tube. You have several of them in the tunnel cross section in order to measure speed, very simply speaking. Let me talk about the modeling. And of course, this is fluid dynamics that you have to do. You have to use the non-stationary Bernoulli equation. It's the Bernoulli equation for non-stationary flows for incompressible flows. So air by itself, of course, is compressible, but since the flow is so slow, it can be treated as incompressible. And you see there is a number of components to be modeled. First of all, it's the flow velocity. So you can see on the right-hand side, there's this term here that stems from the friction. So there's some friction. You probably know the Bernoulli equation. It's proportional to the square of the velocity, of course. Then there is another term that comes from the fans. So there's a number of fans. You can see here there is the fan speed. There is the square of the fan speed. And then there is some funny term here. And this is very important. You might remember that I told you that the lead derivative LG can be 0 sometimes. And in this case, if the fans are windmilling, so if the rotational speed of the fan is just good enough to make this expression here 0, so you can see there's the flow velocity, there's the angular velocity of the fans, there is some constant here. If all this is 0 at this point, so if the fans are windmilling, you cannot control the flow. This is also one problem. And then, of course, linearization does not make sense because in this state, the system is not controllable. And then there is some other term. This is disturbance. So you see some delta P here, because with all tunnels, there's always some pressure drop between the entrance of the tunnel and the exit. So there's always some slight pressure difference. And this is just good enough to shift the flow regime into a certain direction, so to say. Also, then there is some dynamics of these jet fans. So if you just speed them up, it doesn't mean that you get pressure all the way. It'll take some time, so like several seconds, so to say. Okay. So this is how you would typically model something. So it's pretty easy if you want so. Or in other words, if you just if you are confronted in modeling this, you would be able to do it by just looking up the non-stationary Bernoulli equation. And the problem we had to do the nonlinear control in this case is actually seen here. What you see here is actually the corridor. This is the admissible corridor for the flow speed. So you see it's very narrow, and only within that corridor is it possible to achieve this safe kind of flow regime, smoke regime, only within the corridor. If it's too fast, obviously you will just blow all the clouds apart and everything is distributed across the tunnel. If it's too slow, though, on the other hand, then those fumes will actually cool down and move all the way to the ground, and you don't want to have this either. So you see, this is the reason why you have this very, very narrow bandwidth. And only from the airflow velocity in the tunnel, so only from the pressure differences, you already get some kind of significant flow in the tunnel. And you probably notice whenever you're in some kind of tunnel or tube, for example, when you wait for the underground in the U1 underground, the red line in Vienna, when you're in the station, there's always some kind of flow. There's always some kind of flow going on. And let me just skip a few slides here. So this is actually what we propose to the authorities there. And you probably know this. So this is the nonlinear control that you know from the lecture. So there's the input transformation, there's the state transformation, there's the external dynamics. So we really had to explain it to them, because obviously if you tell them, okay, there's your tunnel and we are going to apply some nonlinear transformation, probably people don't feel very easy. So you really, as a control engineer, you also have to show them, you have to convince them that it's going to work, and you have to convince them, you have to make them feel safe about it. Okay, so you have to explain it in some way. And now I'm skipping all this. And of course, there's the state space model, which I've already explained. So there it has a number of states. So this is the actual speed of the system, the flow speed. And then there is some jet fan dynamics, as I've explained earlier, so to say. And then you have to carry out or compute those Lie derivatives. And as I've said before, so x1 is actually the flow speed, x2 is the jet fan speed. And if there is a certain configuration when this expression is 0, you remember what I said a couple of weeks ago, if this is 0, the system is not controllable, and it does not make any sense to linearize it in such an operating point, because you're not going to get anything. And this was the reason why I motivated to them, why we had to do it in this way, if you want so, okay? So there's our diffeomorphism, you probably know it. And exactly from our today's lecture, remember we had the x star, this was the reference trajectory, which followed from the inverse transformation of our reference speed, its derivative all the way to the r minus first derivative. So this is exactly what I've told you today, how you could do it. And from this, you can actually derive a feed-forward control law that tells you exactly how to speed up the jet fans in such a way that you get a nice trajectory of this system, if you want so. And of course, I just told them, if you get in such a situation, then it's a problem, so to say. This is the windmilling situation. So we already had this. Then, of course, we had some feedback control. So this was the 2 degree of freedom control. And let me just show you how this works. So this is a typical result that we got from this tunnel. So you can see this is the time axis. 300 seconds was the limit to reach this corridor. And you see that only by the feed-forward control, so without any feedback and PI control, such a control scheme was already able to reach this safe corridor already like less than 2 minutes after the outbreak of fire. So you see, this was our reference trajectory that we generated for the system. And obviously, there's always some control error, like with our flexible joint, which we had to counteract, obviously. So what else am I going to show you? There are some further experiments. Obviously, I'm not going to show you everything. And this was the actual experiment that we did. I'm going to show you a video with the actual fire. So we did some try tests, if you want, so just with natural flow of the tunnel, of course. And then at some stage, those people from the authorities came to the scene, and we had to do exactly this. Let me show you. So there was a kind of table with this incentive mixture of gasoline, petrol, and diesel. And let me just start the video. So. So in the first part, it's just during the transient, so when the fire has just begun. So you see there is still a plume, a mushroom of smoke forming up, filling the tunnel. So there's no flow. You can see it if you just observe the brim of this smoke, so to say, basin, nothing is going on. So this is just the first couple of seconds. Everything is filling up with smoke. And then the controller started to act. And it took, as you just saw, about like 100 seconds for the steady state to be reached. And you see, this is what we call the back layering. So you can see there's a flow of smoke into that direction. So this is the outward direction. This is a directional carriageway of the motorway. So there's a flow of smoke here. There is an invisible flow that comes from the fire, goes into that direction, changes direction, and goes back. So you can see this is working really nicely, and it's working regardless of the operating point. So if there is some pressure difference in a tunnel, then it still works, because only with the nonlinear control you are able to achieve such a control scheme. Okay, so that actually brings me to almost the end of my lecture today. I think that kind of video and presentation is a very nice motivation to see what you can achieve. So you see, this all looks very complicated, and still the model that we used to control this and the way how it was done was actually pretty easy and simple. And with the knowledge that you just gained in this lecture, you would also be able, at least in theory and in principle, to achieve this. And this is a very nice way to show how control works. So I'm almost at the end of the lecture, and what I would like to do is right now is give you some kind of outlook. There's a number of lectures that we give at our institute in terms of control, which might be interesting to you. Let me just show you this in the last couple of minutes. First of all, this was feedback control. You just attended this. You remember the LEM, the Lunar Module Lander, that I explained it to you. This was from the Lyapunov control that I've shown you. In everything, every time when you model something, question is normally like, how do you get the model? How do you get the structure of the model? How do you get the parameters of the model? We also had this problem with the motorway tunnels. How do we know the friction? How do we know how long it takes for the jet fans to speed up? This is a question that is normally always encountered in almost every system. And we have a lecture that is especially dedicated to that. And this is called Identifikation experimentelle Modellbildung. So it means, how do you get your model or your model parameters from experiments? So we did that with the tunnel, and I'm going to show you this in one or two slides, which I skipped before. With that tunnel, we had a number of parameters like the friction, like some parameters for the jet fan, and also the pressure difference in the portal. And then we had to come up with some experiments for the Road and Traffic Authority in order how to find these parameters. And there are some ways. It's normally formulated as an optimization problem in order to get to these parameters. So normally, whenever you're called to a scene where you have to control something, people tell you, okay, this is my plant, this is my tunnel, this is my whatever, please control it. And then you would ask them, okay, so what is the friction? And they will tell you, I don't know. What is the thrust coefficient of the jet fan? What is the time constant of the jet fan? They will tell you, I don't know. I don't have a clue. I just run it for decades now, but I don't know. And this is where this lecture comes into play, where we are going to show you what are the proper ways to do this. Okay, this is called Identifikation experimentelle Modellbildung. Secondly, something which is also very important. Normally in control, thus far you've only heard about there is a reference value. So there's something where we want our system to be. Today you've heard about trajectories. So how do we design nice transits from one operating point to the others? Oftentimes it happens, and then particularly, for example, in the chemical industry, but also in aircraft, in spacecraft, in space travel, it happens that you do not only know what you want right now for the moment. So this is the time axis here. You do not only want what you want right now, but you also have some idea about the future. Imagine that you launch a spacecraft, you're Elon Musk, you want to launch a spacecraft, and it should actually meet the International Space Station somewhere in space. So you actually know exactly where you want to go also for the future. Or like for this kind of oil refinery, you probably know what is the demanded output of your refinery in the future. Somebody tells you, okay, if the gasoline price is going up, then we are going to produce more, for example. This is one thing. So this is about predicting something which is going to happen in the future. Secondly, in virtually all control systems, there are constraints. There is a maximum power of your spacecraft, okay? In our tunnel, there's a maximum power of the jet fans, for example. There is a maximum value of any states. Let's assume that there is some kind of pressure in this pipe. So there will be a maximum pressure, there will be a maximum temperature, otherwise it's going to blow up. So whenever we do something here, we want to observe these constraints and we want to predict them. So we are right now, and if we do something here, for also even like if you drive your car, you're looking out in front of your windscreen, what is going on? Am I going to hit the guide rail? Am I going to hit another car? No, I'm going to avoid it, okay? So this is the second important thing, constraints in the system, and everything together is normally called model predictive control. And we're going to cover this in the winter term, model predictive control. How are you going to do this? How are you going to use a state space model in order to predict what is going on in the future? And if somebody tells you what you have to do in the future, you're going to observe this control, and you're also going to observe constraints on the system. Also, like, for example, emissions. If you control a refinery, you want to control emissions. So like OMV refinery, which you probably know, it's located in Schwechat. So when you go to the airport, you normally see it. Virtually all of it is controlled by model predictive control, and some of it was actually done by us, by our institute also. So if you're interested in that, it's a good idea to probably also consider this lecture. Okay. What else? This is our parallel lecture, which runs in the summer term. It's held by Christoph Hamedner. It covers most of the stuff that you have heard from my side, but for multi-variable systems. So what happens if there's more than one output to be controlled? What happens if there's more than one input? So look at this helicopter that has like eight rotor fans. You're able to control tilt and pitch and everything. Or for example, the spacecraft, you have to control many different axes, like for example, pitch axis, roll axis. Everything has to be controlled simultaneously. This is the Mehrgrößen system. So if you didn't attend it right now, and if you're just wondering, well, what happens if there's more than one input and more than one output? How can I use it? How can I decouple it? For example, in a chemical plant, if you want to control temperature and pressure separately, how do you have to decouple it? If you increase the temperature, so does the pressure. What can I do about it? So this would be the lecture to attend. And then, of course, this is another lecture, which is parallel digital control. Thus far, everything that you've heard in our lectures was continuous. So we had differential equations, we had continuous control signals, and obviously in our modern world, everything is done by computers, which you see here in this by this aircraft cockpit. And in computers, everything is done in discrete times. A computer is only able to compute such, like for example, a control input every 1 second, every millisecond, or whatever. Normally, if everything runs fine, you can just neglect this. You just assume that you have your continuous control law and you evaluate it every like 1 millisecond and it works. There are other situations, however, where this is not true anymore, and this is the moment where digital control comes into play and where you could profit from attending this lecture. Okay. So I will send this this folder to Alexis Benatier, and he will probably send it out to you, and then you can read the text and probably decide if you want to attend one of these lectures. So all in all, this brings me to the end of the lecture part of the Vorlesungsübung. So the remainder of this course will be dedicated to the Übungen, to the exercises, and also to the lab class, okay? And this will be held by Alexis, or it will be guided by Alexis Benatier. And maybe would you like to say some words to our students right now at this point? It's muted his microphone.
Yeah, basically we already updated students about this lab experiment and the exam, but we'll just give further notification, especially for the exam dates. That will be beginning of June, I guess, but we won't be able to know that before the end of May.
Yeah. So as soon as we have any news as to the exam, we will notify you. And as I said last week, if any one of you has to take the exam earlier for reasons, for example, for if you want to travel or whatever, you just let us know and we will find some solution in that regard. Okay. But for us, I think by the beginning of June, we should know everything. So that should be in about 2 weeks or 3 weeks from now, and we'll let you know. And then there will be the lab class. This is easier actually, because you don't have to attend our lab physically, but we are going to set it up. It will be the inverted pendulum. And then there will be a video camera, and you will be able to design your controllers, do your simulations, then upload your controller parameters, and the experiment will start by itself. You will get a video recording of what happened, and then you will be able to draw your conclusion. So this is much easier actually. Okay. Anything else that needs to be said?
I have a question.
Okay, yeah.
Will the dynamic feed-forward control part be part of the exam?
I didn't think about this. Essentially, I would say yes. I mean, it's not a big deal because it's more or less identical to the feedback linearization. So if you know feedback linearization, you know dynamic feed-forward control, essentially.
Okay, thank you.
Yeah.
I have a question. There will be still 2 exams, right? Or will that change?
It depends. Actually, it depends. It depends on how many or how easily will we get the classroom. Okay. Right now, as seen from the day, it's rather likely that we are only going to have one exam. Okay. We are going to have one exam and then a replacement exam, because otherwise we will have 2 exams and we have to have one replacement exam, which means that we have to get 3 classes, and this will be difficult right now because there are lots of exams that have to be organized by the university, and I think then we are going to run really late.
And when would be the last, how do you say, expectable date for the exam to happen, or for the replacement exam as well?
Right now, I cannot tell because as with the beginning, right now the compulsory exams, mostly from the bachelor degrees, will be organized. Still from us, from the Grundlagen der Regelungstechnik, from the winter term, the replacement exam is still open, so we have to organize it. And only once all these are done, obviously, will we get our time schedule for the exams. Okay. And again, if for some people some of you might lose their scholarships if you don't finish your studies in time, probably, or if any other problem comes about, you just email me and we will organize something. Okay, we will find some way. Normally, if some exams are delayed and some people sometimes threaten to lose their grant, and of course we don't want to have this to happen. Or if you have some, if you're going abroad or whatever comes in your way, then you just tell me. Okay.
Okay. Because for me, the last possible date would be end of July. I'm planning to have an exchange program.
Okay. Yeah.
So
I mean, the end of July is still far away. if it happens that the exam date is too late, you just let us know, either me or Alexis, and then we are going to organize something. Yeah.
I see. Okay,
Probably if there's maybe let's do it like that. Could you just leave us a chat notice right now if you want to finish, or if you have to finish the course, so say before the end of July? Could you just type yes right now? There are 2, yes, 3, 4 persons, 4 people. Okay, I mean, let's wait what happens in 2 weeks. Either it's not a problem anyway because we get the classroom, and otherwise you just email us and then we are going to organize something. So we're going to find some way.
Okay.
Okay.
Just one technical question from my side.
Yes.
In the beginning of the course, Professor Kozek told us that the test contains a practical and theoretical type
Yes.
part.
Mm-hmm.
And my question is, will we be provided with any question catalog for the theoretical part?
No, we don't do that because we just don't want you to give a recipe and then you recite this, because you're not cooks, so to say, if you want. But theoretical questions will be framed in such a way that when you read the book, or if you follow the lecture, and if you understand the basic principles, then you will be able to understand such questions. Okay.
Okay.
Yeah. So they're not like in the very mathematical stuff or whatever. It's just about checking whether you're not only reciting or just solving the exam problems, but if you understood to some extent what is the idea behind. Okay.
So you are not going to examine any special derivations or something like that?
No, not like this. I don't think it makes sense to examine like how to derive something, but let's for example, if we are talking about feedback linearization, for instance, I'm going to bring this up. Hang on, I'm going to share my screen again. So, here's the slides. I mean, we never had any problems with the theoretical questions in the past, so to say. So for example, in the Lyapunov function, okay, if you consider, okay, let's go back there. I'm never good at inventing anything out of the blue. But if you think about the Lyapunov function, remember the coin video that I've shown you. The coin video actually explains the basic principle of the Lyapunov function. We find some function that is always positive, and its derivative along the trajectories of the system essentially should be negative. This is the basic principle. So we're not going to ask you, for example, to prove, there's no proof here anyway. We're not going to ask you some kind of proof, but to explain you, well, what is a Lyapunov function? What is the idea of Lyapunov stability? It's actually explained by a few words which are found here. And you don't have to learn this by heart if you understood the basic principles of the Lyapunov stability, which is given here, then you would be able to show me this just out of the blue if you want. So it's not really difficult. It's a very simple principle if you want. So, okay. Or maybe something else, the Ackermann formula, it just came to my mind. You probably remember the Ackermann formula. Hang on for a second, I'm just trying to find it. Or maybe there's 2 examples. Stability. Why do all the eigenvalues of the system matrix of A have to lie in the left half plane of the complex plane? I mean, this is the answer to stability. And you can either learn it by heart, or you just remember that the solution of this is found as x is equal to some vector u times e to the lambda t. Once you remember this and you insert here, you will find the solution. So you don't have to learn anything by heart. It's just a very simple idea. All those solutions should decay over time. And let me go to the Ackermann formula. Hopefully I'm finding it right now. Hang on for a second. It's too fast right now. Just skipped it. In the Ackermann formula, you know that the controllability matrix plays a role. Here it is, okay? And obviously the Ackermann formula only works if the inverse of the controllability exists, okay? And of course, this is not coincidence, because if the system is not fully state controllable, then you will not be able to assign any arbitrary closed loop polynomial, okay? So you're probably not going to ask you what is the Ackermann formula and you have to know it by heart, but it's better to understand that if the controllability matrix is not invertible, which means the system is not controllable, then you're not able to apply it. You see? Does this address your question to some extent?
Yes. So it's more about logical questions than stupid learning by heart.
Exactly. In the past, we had made the experience that some students just took the exercise book and then tried to solve the problems. And of course, to some extent, you're able to solve them. And we also want you to understand some background. It's pretty much like you cannot fly a jet airliner. You could probably fly it if somebody told you, okay, press this button, press that button, then turn this knob. But you should really understand why it works that way. Okay, and this is what we want.
Okay, thank you.
Okay.
Will the exam be like Grundlagen of Regelungstechnik, like multiple choice, or you have to write full answers?
I cannot remember how we did it last year because I didn't hold the lecture then, but mostly it will be a mixture of these theoretical questions, theory questions, and exercise problems. And because you're not many, I think you're like 20 attendance right now, we are not going to do multiple choice.
I see. One more thing for the lab, is there anything to prepare, or is it like we do the lab and after that we have to make a protocol? And
you will get some very precise instructions on that.
Okay. Okay.
Yeah. And I would really like ask you all to take this lab seriously, not just do it because you have to do it. For me, when I attended control theory, like this was about 25 years ago, the moment I really started to like it was the point when I really saw a lab experiment working. This was the magnetic levitation system. The first time I saw that this really worked was the moment I really liked it. So then it was just more than just mathematics and equations and matrices. And so I would really ask you, give yourself the chance to grow to like this by paying some attention and devoting some time to the lab class. Okay, anything else? That is not the case. So then I would like to say thank you again for attending all the lectures, and I wish you lots of success with the remainder, with the exercise, the lab class, and of course also the exam. And I would really be very happy if I saw some of you back in one of our advanced courses which are starting the winter term. So thank you, and have a nice time.
Thank you.
Thank you.
So we have to stop the recording.